It's sometimes hard and even frustrating trying to define and explain what embedded systems are. Is it about the small size, the small amount of memory, the weak CPU? Is it about the specific functionality? So, for example, this Arduino right here is very clear an embedded system. It has a very small CPU, very little memory, and when you burn it with something, it stays with a very specific functionality. But what about this router right here? On one hand, it has very specific functionality and you cannot just install things on it. It has a very rigid API. But on the other hand, some of those routers have a substantial computing system on it with a lot of memory, a lot of CPU power, and some of them actually run embedded Linux. So in this series of videos, I will talk about the definition of what embedded systems are, but most importantly, what is special about them, developing for them, producing them, and so on. Keep watching.
So, what are embedded systems? Let's see a great example before we go to more formal definitions. Look at this iFi SD card, a product that can both store and transmit its content over Wi-Fi. This tiny product has three systems embedded into it. This chip contains an ARM CPU with memory, hardware, and everything. It can be looked at as a small computer capable of running embedded software, also called firmware. Firm is because it cannot be arbitrarily replaced by a user, although it can sometimes be updated, as we will discuss later. This chip is a WLAN SoC or System on Chip by Marvell. It also contains a microcontroller, a CPU, and is a tiny system by its own right. This chip is a Samsung eMMC device, a storage device. It too has, you guessed it, a CPU on board that runs firmware. So in fact, this tiny product is actually a platform with multiple subsystems having inter-system interactions in order to fulfill a task. We can find embedded systems everywhere, managing tiny devices like a USB thumb drive through controlling critical systems like traffic control, cars, appliances, and even weapons. The production volume of microcontrollers or MCUs that are at the core of every embedded system continues to grow. Right now, it is already at the tens of billions annually. A modern car has dozens of embedded systems in it, with some surpassing 100 MCUs. In some cases, the joint count of lines of code in such a car amounts to around 150 million lines of code. For every person in the US, there are roughly a dozen systems out there. Embedded MCUs dominate the CPU world, with close to 99% of CPUs actually being embedded MCUs. What are the characteristics of embedded systems, especially small Internet of Things devices or other small embedded systems? We start at the upper left corner and go clockwise. It has a targeted task, and for that a tailored solution is created, unlike general purpose computers. To fulfill that task, it has targeted APIs and interconnects with other subsystems. It is highly constrained in space, cost, and power. Accordingly, it has minimal CPU power, memory size, and storage. It has a more involved development model compared to regular software, which we will investigate later, and many times it is part of a bigger platform and works with other subsystems on that platform. But hold on, there are systems that fit only partially into that description and are still considered embedded systems, at least to some degree. Take a look at this network attached storage device, or this set-top box device, or that router. Some of those devices are big enough to actually be more similar to big computers in terms of computing power, operating systems, and hardware. They are usually connected to AC ports, so they don't care so much about being power conserving. On the other hand, they do have firmware that cannot be changed under most circumstances, except by manufacturer updates. They have a narrow API, even if not as narrow as in smaller systems, and in general are still far from being a multi-purpose computer. So I like to think about systems as being on a size spectrum. Just to be clear, the size here is not the physical size of the hosting system. It is the level of adherence to the classical characteristics of embedded systems that we have described before. On the leftmost side, we have the smallest systems with just barely any CPU power, tiny memory, and hard power constraints. On the right side, we have the other extreme, a full multi-purpose computer with a fully dynamic OS and application freedom, and without too much worry about power, size, or cost. In this talk, we concentrate on the left side. What we discuss in this talk may gradually become less relevant as you start looking at systems closer to the rightmost side of the spectrum. Perhaps the most important characteristics of embedded systems is this. It is a system tasked with a specific problem, employs a specific solution with tailored resources and design. If you take anything from this talk, please take this. So we have given some thought to what embedded systems are and about special characteristics they have. Let's see some of the challenges that are derived from those characteristics and how we can deal with them. So we begin with differences in how we build firmware and later how we execute it. We later look at how embedded operating systems are different than the big operating system we all know. We continue to differences in debugging and also in logging, which is a relative of debugging but has other very important usages. We then address three of the most challenging issues in embedded systems: how to update firmware, how to make the system survivable, and a little about how to make it more secure. When building firmware or embedded software for embedded systems, we find additional things we have to consider. When we build regular software on a desktop PC, we usually get directly a product in the form of an ELF file or other similar formats that includes all the build products, the runtime binary, linked and ready, the debug info if we chose to include it, and other metadata like code relocation data, section data, and so on. The operating system takes care of loading such binaries, and it's usually seamless to us. When building for embedded systems, we first have to account for the target system being of a different architecture than our work machine. For example, we build on our Intel-based desktop, but the firmware is destined to be run on an Arduino which has an AVR microcontroller. The resulting binary cannot run directly on the desktop CPU as it includes machine code and other things that match the AVR architecture and not our CPU's architecture. Building on one architecture while targeting another architecture is called cross-compilation. One other difference is that many times we will have to be more involved in the build process and explicitly do things that we get for free on big systems. Three examples are the memory layout, which we may have to craft manually, the removal of unnecessary metadata, unlike in big systems, and finally the crafting of a burnable image. Let's look at a typical build process. A typical build process may look like this. We cross-compile to the target's binary and then link with a linker script that lays out the binary in memory according to our specific requirements. From the link product, we remove the unnecessary metadata like debug symbols, relocation data, and alike. We are left with just the runtime code or binary. To that, we may want to glue initial data for a system, unique identifiers, and feature information for the system to consume during runtime. Now we have a finalized image we can burn on the target. Okay, so we have successfully created an image. Now we want to run it. Again, it cannot run directly on our work machine. We need to get it into the target platform and run it there. But how? So obviously, we need the image to somehow get from the work machine to the target, right? One way is to use a bootloader like what Arduino has. It requires the system to come pre-installed with a piece of firmware already running on it that will handle the communication and the image transfer into the system storage. Another way to get the image onto the device storage is to burn it directly with an ISP, in-system programmer. This device works directly at the hardware level and does not require a pre-installed firmware, Potentially, this method is more powerful than the bootloader method, since this bootloader can have restrictions. For example, a piece of firmware already running on the system may be restricted from writing to certain parts of the storage for security reasons. This is, of course, also the way to get the bootloader into the system. Another possible way is to use a mass burner that can burn the storage devices directly, so they can later be placed, perhaps soldered, into systems. Alright, so we have got our image onto the system for execution. Let's talk about how work with such system can look like in the real industrial world. If things are being developed in series, for example, if the hardware is purchased off the shelf, it means it is ready before you start writing your first line of firmware code. In that case, we are in a good shape since the hardware is stable and we can start writing firmware right away. However, if our company is also doing the hardware, or if an external vendor is building special hardware for us, it may mean that the firmware developers will be sitting on their hands for quite a while, waiting for hardware to run their firmware on. The same goes for firmware validation engineers. All this manpower will be waiting for the hardware to come. To address this problem, there are methods to working without the hardware being fully ready. Using such methods, firmware developers and validators can start working much faster after project conception.
Those methods are called pre-silicon development methods because we start working before our hardware, aka silicon, is ready.
One way is simulators. A hardware simulator is a piece of software simulating the behavior of hardware with various trade-offs of speed and accuracy. Here we see the Atmel Studio that can simulate the AVR microcontroller, but not necessarily every piece of hardware that is on it. So one advantage of working on a simulator is that it is ready early, potentially before the real hardware is ready. That allows early beginning of firmware work. It also has less overhead than a real system. You don't have to go through burning, electrical malfunctions, size restrictions, and so on. A simulator can also allow for powerful debugging features. For example, even if the real hardware does not support watch points, also known as data breakpoints, you may still be able to have it on the simulator for that system. Another example is getting prints out. While challenging on some systems, it is potentially easier to do on simulators of those systems. Validation can also enjoy special simulation features. Beside the early start of the work, they can, for example, run many simulator instances to create a stress test. With real hardware, it can prove much more difficult. Without any real materials, and with some hardware platforms being extremely expensive, using simulators may reduce costs. That said, some simulators may have high licensing costs. There are also downsides. A simulator can rarely give a very accurate reflection of the hardware for several reasons. It is generally less accurate since it cannot simulate every bit of what is going on real hardware. Hardware is a physical beast and have some disorder in the way it runs. So on higher levels, it may not affect execution badly, but think about thread scheduling, for example. They may schedule a little bit differently on real hardware, while on a simulator you may see them do the same thing over and over again. On top of that, a simulator is slower than real hardware. The more accurate it is, the slower it gets. And on top of all that, it may be impossible to simulate all parts of the system. For example, if the system is very big and complex. Another option for pre-silicon work is an FPGA. Here we see a development board by Altera. The other big player in the market for FPGAs is Xilinx. This is a development board built around an Altera Cyclone 3 FPGA chip. An FPGA chip is a chip with no fixed logic. It can be programmed to assume different logics. This is unlike the regular chip, ASIC, which stands for Application Specific Integrated Circuit, which has fixed logic that cannot be changed. For example, on the left, we have an Atmel ASIC with fixed logic, the AVR microcontroller. If we have the details of that logic, we can make the FPGA become an AVR microcontroller.
For that reason, FPGAs can be used for pre-silicon development.
While the hardware is still being developed, developers can take hardware logic that is not yet fully baked, put it on the FPGA, and create an execution environment that has a strong relation to the final hardware product. So, an FPGA model of our ASIC chip can be ready early, which is good. Possibly, since it is based on the real hardware, it can be closer to the real hardware than a simulator. As a bonus, when the firmware runs on those FPGA models, it can give feedback about hardware bugs. So we have a sort of symbiosis between the firmware and the hardware development and validation. On the downside, FPGAs can be very expensive, have even more overhead than normal platforms, and an FPGA is generally slower than the equivalent ASIC. On top of that, FPGAs have limited space for logic, and the implemented logic consumes more space on an FPGA than on an ASIC. For that reason, it is very possible that we will not be able to simulate the entire ASIC on an FPGA. Potentially, several FPGA chips can be combined to implement big logics, but that can become really expensive.
You can find a lot of information about FPGA in my FPGA for Beginners video. At this point, you are probably dying to know what is special about developing for embedded systems. And this is exactly what you're going to get in the following videos in this series. Please like this video and also don't forget to subscribe because there is more stuff like that coming your way. See you.